All right, we're live. All right, shout out to the Grifster and Emma. Thanks for the gifted subs.
That's so good.
How many gifted subs do your parents get you for Christmas typically, Julia? Okay. Sorry to hear that. Okay, we left off on 16, I think. So there's like a hammer here. Hammer time, indeed. Hammer time, indeed. So we're going to find the center of mass. A little bit of a technique here that is pretty intuitive. So there's an 80 centimeter long rod here. Okay. Now, I guess we're in the habit of just using meters, so we might as well do that. So 0.8 meters, and then there's this cube here, which is 20 centimeters by 20 centimeters by 20. So that's 0.2 meters. Made it. I want to make roughly the scale. That's 0.8 meters. Everyone okay with that? Makes sense? Okay, so the question is, where is the hammer center of mass? Where is the balancing point? So the trick to this is to analyze these two things separately, because when if you're talking about hanging some of these masses off of like a long rod, then you can, for all intents and purposes, treat this like a point mass, like a single point. But when all the mass is distributed over this whole thing, it's not so easy. So here, someone take a guess. If I just want to analyze this rod here, where do you think the center of mass is? That's in the middle. So the trick is you pretend like the rod is massless, but that all of its mass is concentrated at the center. So you go, well, I'm going to pretend like all 5 kilograms is just concentrated at the center. Does that make sense? It's not really obvious why that is the case. To prove why that's a valid approach, you have to use a bunch of calculus. I hope it makes intuitive sense, though. How about the cube? Where's the center of mass of the cube? In the center. Very good. So you take the cube and say, well, I'm going to pretend like for the cube, all of its 15 kilograms are concentrated at the very center of the cube. Okay? And so now basically what you do is you kind of pretend like this is an ultra lightweight material with a single little ball of 5 kilograms, and same thing for the cube. Okay? And so let's call this position 0, and let's calculate the center of mass. Also, let's talk about a symbol that some of you guys maybe have not seen before. The center of mass. Center of mass is so it's the sum. Who's seen that symbol before? Who remembers the name of it? Huh?
Sigma?
Sigma, yes. That symbol is sigma. Yes, very good, very clever. That was Noah's favorite, Noah Golan's favorite unit of the year, because sigma sounds like that. Okay. Sigma, now what do you add up? You add up all the mass times position. So you think of like X as being the position. And then you divide that by the sum of all the masses. Okay, that's kind of like a loose notation, but we're not going to get into the business of like the precise notation. If you're curious, it would look something like this. It would be like you'd go sigma. You'd say like I equals 0, m sub I times x sub I, all the way up to n for how many bodies there are. So if you want, I just meaning the subscript. So you'd start at the 0th item, and the first, and the second, and the third, and the fourth, all the way to the nth item. Anyway, this means the same thing. So just sigma means sum. It means add up all the objects. Okay. So anyway, okay, let's do it. I go mass. So 5 times what? What's his position? 0.4. Do we all feel okay about that?
Yes.
He's halfway along this rod, right? How about this guy? What's his position? 0.9. Everyone okay with 0.9? Okay. And then you divide that by the total mass of the system, which is 5 plus 15. And so Mr. Quackulator would be helpful here, I think.
Working on it. 0.775.
That's where the center mass stuff. 15.
Everyone agree with that? Okay. Now let's interpret the number. What does that mean? What does it mean?
Between those 2 points is where the center mass.
So hopefully you can look at this and say it's like there, right? Because we defined this as position 0, so position 0.775 is awfully close to the end here. So what that means is you could put your hand here and balance it.
That was a bright number. Yeah. Or a very small man.
What do you mean? It's a meter long. Fine.
He said the scale was still
You said the scale.
Yeah. Those lines.
Okay. All right, let's move on. So hopefully today we can get to what does this have to do with what does it have to do with momentum? Momentum. All right, look at 17. 17 says you got 2 blocks. They have different masses. They start at the same position, but they have different velocities. And we're going to write an equation for the system's center of mass. An equation describing this. How does the center of mass move over time? So, okay. Position 0 is where they start. So this is at time 0. They both start here. There's these 2 blocks, right? One of them is 20 kilograms. The 20 kilogram block is traveling how fast? 4 meters per second. And then there's a 30 kilogram block that's traveling 6 meters per second. Does everyone understand that?
Mm-hmm.
So let's think. How could we, how would we write an equation? Where's the center of mass at the very beginning? 0, right? Make sense? How about later on? Well, later on, the 30 kilogram mass is going to be, say, over here, and the 20 kilogram mass might be like right here. And then where do you think, will the center of mass be closer to block B or block A? It'll be closer to block B because B is heavier. Yeah.
They're traveling in opposite directions.
Oh, thank you. Yeah. Missed that. Thanks, Kate. What would I do without you? I would make lots of mistakes. Thank you. They're going the opposite direction. Sorry, guys. Boom. Just testing you. Okay, same idea. So at a later time, block B will be farther away from the starting point than block A. And so over time, where will the center of mass be drifting? It'll be heading to the right, yeah, towards B, right? So we have an equation, right? How do you write the center of mass? You multiply mass by position, right? Add up mass times position plus mass times position, and you divide by the total mass, right? So let's do that. What's block A's position function? So let's say position of block A. He's going this speed. No one? Please. What? Anyone?
Huh?
I think Caleb should say his answer.
Negative 14. Right? He's starting at 0. That's his velocity is negative 4, because Kate corrected me there. They're going to the left. Okay? So his position function is, right? His table of values would go 0, negative 4, negative 8, negative 12, looking at integer values of t. And this guy, his position function would be 6t. Right? Okay, so let's write the center of mass. So the position of the center of mass would be, well, we got to go mass times position. So mass of block A times the position of block A. Make sense? Plus the mass of block B times the position of block B, and divide that by the total mass of the system, which is 20 plus 30. I think I'm going to kick this cord and send this computer flying at some point, so hopefully I can avoid that. But it's the battery's dead. Okay, anyway, are there any questions on that? Okay, let's simplify that equation, because certainly we can write it a bit nicer than that. How many t's? Negative 80. How many t's there?
180.
Positive 180. So how many t's total on top? 100 divided by
50. So.
It's a pretty nice result, right? Let's interpret that. What is that's the center of mass's position function. So what's the velocity? How fast is the center of mass moving? 2 meters per second. Yeah, sort of coincidentally, if you add those up, you get 2. Or if you subtract their absolute values. I don't know if that's always going to be the case, but. Huh?
It'd be cool if it was.
There is something to take out of this, which is to me, I think think about where the 2 kind of comes from. It's this guy 20 times. What's the significance of 20 times 4? That's the value. What's the significance? What's that called when you multiply the mass times the velocity?
Acceleration.
Displacement. No, that's wrong. That's wrong.
Momentum. Momentum.
I didn't say that magical force that keeps the block moving.
Yes,
Yeah.
yes, the magical force that's required for things to move. That totally exists.
Dark matter.
Dark matter. Yes. E equals mc squared was the answer. All right. No, the momentum. So his momentum was 80, or negative 80, rather. His momentum, right, was positive 180. So when you think about these multiplications that are getting done, right? That has to do with momentum. So you could think of negative 80 plus 180 as the total momentum of the system. So what you kind of saw here is like, where did this velocity come from? It was the total momentum divided by the total mass. Okay. All righty. That's my really clever lead in to number 18, I guess, because we're going to analyze the same thing, doing that's how they make us do it in the big leagues. Big league, the big leagues. No numberies, no more numbers. Okay. Okay. So, same kind of question. Now, it doesn't specify if they're going left or right, but we're going to see it doesn't really matter if they're going left or right. Let's just, for argument's sake, say they're going in the same direction. Oh, by the way, here. I should just show this to you real quick. Goodness, what's that? Just a good visualization here. I'm just gonna. What were the speeds in the last one? Was it 6 and 4? 6 and 4. Sorry. I want to make a point. I don't remember the syntax, I guess. Hold on. Make a point like, okay, make a point. I wanted a slider. Slider. There we go. I want a slider. Okay. Okay, great. So all I wanted to show you here was, if you wanted to visualize the center of mass moving with the system, the other one was -4, right?
Mm-hmm.
So I have them set to move along the x-axis here. And so if I say go, oh, that's really fast. Slow. That's like when you guys have online school, you watch the video on slow speed, right? To really absorb the information. Okay. But you see what I'm looking at?
Yeah.
Okay, so that's just the two masses moving. But what if I wanted to also look at, we calculated the center of mass, right? So the center of mass was 2t. I'm using A because Desmos was kind of being weird about me using t as a slider. But look, that's what happens. So notice, as time goes on, who is the center of mass closer to? This guy or this guy?
This guy.
This guy, a little bit closer. And as time goes on, that disparity kind of grows. But he always kind of maintains a certain like ratio, if that makes sense. He always maintains the ratio. So what we're gonna start talking about pretty soon is, what would happen if you, the observer, was traveling along like a cart, a train that was going this speed? What if you lived here? What would things look like from your perspective?
You probably look like we were chasing one dot and the other one's going the other way.
Yeah, so yeah, I think about how, like, from your perspective here, he would be going slower because you're chasing him, and he seems to be going faster because you're moving away from him. So that's a big idea that Alfred Eisenstein used. That's how that's actually kind of like it. Well, you guys have all heard of Albert Einstein, right?
Yes.
You know, it's
French guy.
the French guy, yeah. What's he famous for? Well, he's famous for a lot of things.
He created gravity.
Yeah, he invented. Yeah, he created gravity. Very good.
Invented the light bulb.
That's one thing he's famous for is, well, you guys know about, there's a
Mona Lisa.
theory of gravity. You guys know about that, right?
I'm pretty sure you put
You might not know about
You put a coin on, I heard that Einstein put a little key on a kite and sent it up into the sky.
Yeah, that was, yeah.
I was the first man on the moon.
Yeah. Well, anyway, there's like, yes, forget it. Okay.
Is he the guy in the wheelchair?
Yeah. All right. Anyway, you can, I guess if anyone cares, you can look at, there's a difference between the law of gravity and the theory of gravity. Newton is typically credited with discovering the law of gravity. Oh, we got some mass here and some mass here. How strong is that gravitational attraction going to be? Alfred Eisenstein came up with the theory of gravity, which is to explain what really is happening under the hood there. Anyway, okay, so 18 says we got, if you live on a number line, there's the origin. So for our purposes here, we're just going to say that they're traveling in the same direction. So here's going to be M1, here's going to be M2. Okay, so M1 travels with velocity V1, M2 travels with velocity V2. Okay, and they're both starting at position 0 at time 0. All right, so position 0, that's at time 0. So let's do the same thing we did before, right? What's the there are two functions, right? So you might say something like the position of particle 1 is his velocity times time, and the position of particle 2 is his velocity times time. No one's confused by that, hopefully, right? So let's write the center of mass. Position for the center of mass. Okay, so you go mass times position, right? You're going to add up all the mass times positions. So mass times position would be M1 times V1 times T. There's his mass times position, plus, same thing for that guy, mass 2 times position. Now there's a critical thing here. What do these guys have in common? The T. It's the same T, so that the system's evolving on the same time frame. So that's all divided by total mass, right? M1 plus M2. Everyone okay with that? Okay, and then so from here, we could factor out this T, right? Common factor. So my position of the center of mass is, let's factor out the T. So M1 V1 plus M2 V2, all divided by M1 plus M2, all multiplied by time. Does everyone understand how that T got factored out there? And why it's not necessarily on top anymore? I could have put it on top, but it's just as fine to put it on bottom. Okay, there's part A. All right. Ready for part B? It's going to be extremely complicated. No, not really. Just kidding. How many of you guys see what's going to happen here? Why it's going to be easy? If we want to rearrange this equation to find the relationship between.
Just like the, yeah, like if you need to find the total mass, and you just do the mass out. You get them on the outside.
I think it's easier than that. There's not much algebra that's left. Where's the total mass? So this question is asking us to relate three things. We want to relate the total mass, so M total. We want to relate the total momentum, so P total, and the velocity of the center of mass. Does everyone understand how that's what the question's asking for? It's what's the equation that relates those three quantities for this system? where do you see the total mass in there? Right here. Okay. Where do you see the total momentum? Momentum 1 plus momentum 2, right? And then how will I get the velocity of the center of mass? No? You see?
Yeah.
If I divide by t, right? If I divide that t to this side, then I'll have position divided by time, which is going to tell me the velocity, right? So what I get is that the velocity of the center of mass is equal to the total momentum divided by the total mass. You feel me? But wait. Oh, the sun. Yes, it.
Isn't momentum the lowercase p?
I think it's lowercase.
I'm
You're right. Yeah, you gotta be careful. Momentum is lowercase p. I don't know. I should maybe I'll try to draw it better. I don't think I when I draw uppercase p, I go like I try to make it like make it more. Although it kind of looks like a row, honestly. A row is this. That's a Greek letter. They use that sometimes for you're doing coordinates, three-dimensional, spherical coordinates. Okay. Now, does this look familiar to you? Hopefully it does. Right? So we started off this unit with a very basic definition, which is that momentum is defined as mass times velocity. But what I've just shown you is that for a system involving multiple bodies, I know I just showed it to you for 2 bodies, but it turns out I'll spare you the rigorous proof of n bodies, but it's true for any number of bodies that the total momentum of a system is equal to the total mass of the system multiplied by the velocity of the center of mass. Isn't that a beautiful result? Come on, that's pretty nifty, right?
Yeah.
Okay, well. Anyway, so a neat result of that, if you think about what this means, this is getting ahead of ourselves a little bit, but it's like if you say you shoot a rocket or a cannonball or something, what kind of path will the cannonball take? Parabolic path, right? But what if the cannonball explodes like here? Say the cannonball explodes into like 10 pieces. Doesn't that become immensely complicated to model that? Yes, if you care about each piece, it's extremely complicated. But so these pieces are all going to shoot off in their own directions, right? But what would have to be true is that the center of mass of all those pieces would have to preserve. If you could track the center of mass of all those pieces, that center of mass would continue to follow that parabolic curve. So
That's really cool.
okay.
Like even with, well, I guess air resistance and stuff would throw it off.
Yeah. Yes. Definitely. Speaking of which, I mean, if you want to be really actually on someone, you can say how this path technically isn't parabolic. It's elliptic. It's elliptical because the whole parabolic path thing is derived from an assumption that the ground is flat and that gravity is constant, which is a very, very, very good approximation. Like that's for all intents and purposes, if you're on the surface, if you're anywhere near the surface of the Earth, that's 99.99999% accurate. But technically, the ball is in orbit around the center of. Well, actually, the cannonball and the Earth are both in orbit around their common center of mass. So, if you want to really just,
Doesn't have to explain that.
Facts and logic.
Oh, like,
Okay, well, all right, so that's sort of the groundwork for what we're going to do for quite a while there, using that fact. Because what that allows you to do is, in practice, or let me ask you guys, maybe you guys have a good intuition for this. How difficult, which of these three quantities, let's say you're analyzing a system, say two blocks are going to like bonk into each other, right? Which is the easiest thing to calculate? Which is the hardest thing to calculate around here? Do you think it's hard to calculate the total mass usually? No, you just add up the masses. Do you think it's often difficult to calculate the total momentum?
I mean, it's harder than mass without.
Right, pretty straightforward. This is the one that's often like pretty tricky to calculate indirectly or directly. So what we're going to find, what we're going to do usually in practice is calculate this directly, pretty easy, calculate this directly, and then make some inference about what the center of mass is doing. So, okay, man, I can tell you guys are enthralled with this.